Let's talk more formally now about the idea of a conic section. So hopefully you just watched the demonstration where we played around with the angle at which we shone a flashlight against a wall to see what sorts of different geometric shapes we could make. The key here is that a conventional flashlight distributes its light outwards in a conical shape. So when we took our cone of light and allowed it to intersect a plane, usually a wall or a window, we produced different shapes. So when we pointed straight at the wall, we ended up with a circle. If we tilted a little bit, okay, if we tilt from side to side, the circle becomes a little bit stretched. We end up with what we call an ellipse. Not eclipse, ellipse. Okay? Don't call it an oval. An oval is more generic a term. Okay, we're going to use the precise term ellipse. And if you pointed them even more steeply along the wall, you would end up with a U-shaped curve, like this. Okay, probably our favorite U-shaped curve is a parabola, but we might also get what we call a hyperbola. The different slices through the cone that we produce are called conic sections, and there are these four basic types. You can either get a circle, more generally an ellipse. If you allow the curve to open up, you get a parabola or perhaps a hyperbola. Now these conic sections have been studied since ancient times, as you can read here. They are actually really useful mathematical objects. For one thing, in terms of Newtonian mechanics and how different bodies move through space. Typically, if a body is moving under the effect of gravity, it will follow one of these orbit paths. So think about the solar system. When you see that classic picture, the planets are following either a circular or usually more often an elliptical orbit, an ellipse. But if you have some asteroid or comet that comes flying by the sun, it will either be on a parabolic path or a hyperbolic path. These shapes also have very interesting reflective properties if you make mirrors out of them. And so in terms of astronomy and telescopes, there are lots of really fascinating uses for these conic sections there too. So let's formalize the construction of our conic sections a little bit more. First things first, we're actually going to consider what we call a double napped cone. Okay? The nap is just 1/2. So our flashlight just produces this one single upward piece of the cone, but if we keep extending that cone downwards, we also get a bottom half too. Okay? There are these two sets of lines called generator lines. Okay, here is one, here is the other. When we rotate those lines about the central axis down the middle, we produce this double napped cone. Okay. The reason we do this is it allows us to extend the domain that we're looking at and allows us to discuss these conic sections in greater and therefore more useful generality. The one thing I haven't talked about is this central point here in the middle where the two generator lines meet. That is called the vertex of the double napped cone. In theory, we allow this cone to just extend indefinitely upwards and downwards so that our parabolas and hyperbolas again have as general a domain as possible. So, as we've seen, to produce our conic sections, we allow a plane to pass through, to intersect our cone and see what curve we produce. Okay. Very importantly, when we do this procedure, the plane is not allowed to meet or intersect the vertex of the cone. If we do that, we end up getting what we call a degenerate conic. Okay, these degenerate conics will not be nearly as nice. They won't have such useful properties as the non-degenerate conics. So let's see what can happen. I'm going to put a link to a video that will show you an animation of this plane moving from a non-degenerate conic to producing a degenerate one, so you can see it come to life. But so I'd encourage you to pause the video after this discussion so you can go and see those animations. But for now, let's see what happens. So in this first picture, we're producing a hyperbola. Okay, so I'll try and draw it on. That's how we're intersecting the cone. Now, if we take that vertical plane and start to move it to the left so that it meets the vertex of the cone, you can see, hopefully, it's going to produce two vertical lines. It will actually meet along the generating lines of the cone when the plane intersects the cone. Okay. When we have a parabola, okay, which is the other U-shaped curve we might have, there's the parabola we've produced. This happens when the intersecting plane is running parallel with one of the generator lines. So if we move the plane so that it intersects the vertex, we actually capture the entire generating line. That will be the intersection with the plane. So we've gone from two of the generating lines when we degenerate the hyperbola to one of the generating lines when we degenerate a parabola. For an ellipse and a circle, it's the same for both cases. So here's our ellipse, here's our circle. As we move those planes vertically to eventually hit the vertex, you can see the only point of intersection between the plane and the cone is at the vertex. So at the bottom here we have these three possibilities. You can see we have, for circle and ellipses that we've allowed to degenerate, we produce a point. When it's a parabola that we have allowed to degenerate, we get one line. And when it's a hyperbola that we've allowed to degenerate, we get two intersecting lines. So this would be a great point, if you haven't already, to pause the video and go and have a look at the link below. So we're going to begin our discussion of conic sections with the circle. Okay, that's one that we've definitely seen before. Think back to geometry. So the definition of a circle is all the points in the plane, x, y, that are a fixed distance from some center point, which we'll call, h, k. Okay. That fixed distance that we're talking about is, of course, going to be the radius r. So those two ingredients totally cook up the circle. As soon as you tell me what the radius and the center are, the rest is history. Well, and remember here we're just emphasizing that a circle degenerates into a point. So since baked into the definition of circle is this idea of distance, we can use our old friend the distance formula to find an equation for circles. So let's remind ourselves of these two formulas. So if we are given 2 points, x1, y1 and x2, y2, well, the midpoint formula was we just took the average of the coordinates, so x1 plus x2 over 2, and then we'll take the average of the y coordinates, y1 plus y2 over 2. That gives us the coordinates of the midpoint. To figure out the distance between the 2 points, d, remember that is the positive square root of the sum of the square of the differences. So x2 minus x1 squared plus y2 minus y1 squared. So as a basic application to see how these formulas are useful, let's look at this example 1. So we're told that a diameter of our circle has endpoints 5, 4 and 0, negative 8. So that's going to be one of our diameters, and we're asked to find the center and the radius. Okay. Well, remember, a diameter is a line that passes through the center of the circle, so the center is going to be the midpoint of that line segment. So we can just use the midpoint formula to find the center. We'll use the midpoint formula to get, we're supposed to take the average of the x-coordinates, so that's 5 plus 0 over 2. The average of the y-coordinates, negative 8 plus 4 over 2. That gives us 2.5, comma, negative 2 as our center. Okay, that's our h, comma, k for this particular circle. So for the radius, we need to take the length of the diameter and half it, right? So let's find the length, the distance d between these points. So we'll take the square root of 0 minus 5 squared plus negative 8 minus 4 squared. When we do that math, we should get the square root of 169, which is, of course, 13. So thus, the radius r, that is half the length of the diameter, so that's 13 over 2, that's 6.5. So that's our radius. So here we see the standard form of the equation for a circle. Okay, it's x minus h all squared plus y minus k all squared equals r squared, where h comma k is the center of the circle and r is the radius, and x comma y is some point satisfying that equation and therefore lying on the circle. So the way that we can derive this standard form is simply by drawing a diagram for a circle whose center is h comma k and whose radius is r, and applying the distance formula to that line segment, right? Pythagoras kicks in and tells us r squared is the horizontal difference squared plus the vertical difference squared. So that's the standard form. For general form, all you're going to do is expand these brackets out. So if we expand and gather like terms, we'll end up with something that looks like ax squared plus by squared plus cx plus dy plus some constant e is equal to 0, where a, b, c, d, and e are real numbers. Okay. If you're given an equation in general form, how do we get back into standard form? Well, that's a little bit more involved, but not too bad. All you need to do is take your x terms and complete the square, then take your y terms and complete the square there, and then any constants that get left over, you can simply absorb into this e over here at the end. So it really is perfectly within your power to pass between standard and general form using the methods that we've seen so far this year. So with the example that we just saw, okay, we worked out that the center was, let me remind myself, 2.5 -2, and the radius was 6.5. So thus, the equation for that circle is x minus h all squared plus y minus k all squared. So that double negative becomes a positive. And then we're supposed to square 6.5. So that'll get us 42.25. Let's look at example 2 here. So we're given the centre and the radius. We're asked to write down the equation and then state the domain and the range. Well, first things first, let's write down the equation. We remember standard form looks like x minus h all squared plus y minus k all squared equals r squared. Well, for this example, what do we have? We have h is 0, k is 6, and r equals 1. So that, when we substitute in, we'll get x squared plus y minus 6 squared is equal to 1 squared. Nice. Okay, well, in order to find the domain and the range, let's draw a little sketch for ourselves. So the centre is 0, 6. So that is there, and the radius is 1. So let's extend 1 around that centre. So we can go 1 down, 1 up, 1 to the right, 1 to the left. And then we can fill in the rest of the circle. It's not necessarily the most beautiful circle we've ever seen, but that's okay. And now we can figure out, right, by adding 1, we'll see exactly what these relevant coordinates are. So when we fall down by 1 and rise up by 1, we get 5 and 7. And when I go 1 to the right and 1 to the left, we get 1 and -1, respectively. So it's asking for the domain and the range. Remember, any graph that you can draw, we can think of as being the graph of a relation, and relations are mathematical objects that have domains and ranges. So we can ask and answer that question. So if I take the domain of my circle, I'm drawing a little circle with its centre there as a decoration. This is the set of possible inputs for our relation, for our circle. So remember, inputs correspond to the x coordinates. So what are my possible x coordinates for this circle? You can see the possible x coordinates lie between -1 and 1. Now, -1 and 1 really do occur as x coordinates, as inputs, so I should have square brackets there. For my range, we're asking the analogous question, but this time about our outputs of our relation, our y coordinates. So here, what are my possible y coordinates? I see that they stretch between 5 and 7. Again, 5 and 7 really do occur as outputs, so we'll have square brackets. For the final example on this page, let's have a look. We're being asked to write the equation of the circle in this graph and state its domain and range. Well, we've seen standard form for a circle is x minus h squared plus y minus k squared equals r squared. So we need to make sure that we extract h, k, and r from this graph of this circle. So we can see here the centre is at 2, 6. So the x coordinate is 2, the y coordinate is 6. What is my radius? Well, the best radius that I can see to take is the one that goes over here. How many units do we pass? We go 5. So the radius is 5. Substituting in 2, our standard form, we get x minus 2 all squared plus y minus 6 all squared equals 5 squared, that's 25. So that's the equation of our circle. Again, we're asked for the domain and the range. This is just asking for our set of possible x coordinates and our set of possible y coordinates. So you can see the x coordinates extend between -3 up to 7, and the y coordinates extend from 1 up to 11. You can see if you zoom in real close on this circle that some of the points are a little bit off, but for simplicity we're assuming that these points really do go through the points on the grid. In this next example, we're again being asked to write down the equation of a circle, but we're being given the information in a different way. We're being told what the centre is. It's the point -3, 5. So let's throw down a little sketch that will help us. -3, 5 is something like there. And we're told that we contain the point 9, 10. So 9, 10 is something like over here. Well, this is the centre here. So this point must be part of what the radius sweeps out when we travel around to produce our circle. Okay, we've gone off the corner, but that is okay. So again, for standard form, what ingredients do we need? We need to know the centre. Well, that's good because we've been told the centre, but we also need to know the radius r. Well, in this picture, you can hopefully see from the centre out to that point, that's exactly a radius of the circle. So what do we have? We have that x plus 3 all squared plus y minus 5 all squared is equal to our unknown radius squared. Well, what additional piece of information have we not used yet? Well, that we have this point 9, 10 on the circle. Let's call that x, y. We can substitute this into the equation that we just wrote down and solve for r. Now you could use the distance formula to calculate the length of this line segment, and that would give you your r, but the distance formula is already wrapped up in the equation that we've written down for this circle, so we may as well just use that to be a little bit more streamlined. So I won't show all the working here, but if we substitute x equals 9 and y equals 10 into this equation, we will get that r is 13. So thus our equation for this circle is x plus 3 all squared plus y minus 5 all squared is equal to 13 squared. That's 169. Now this next example you can see is given in general form, not in standard form. So it's not so immediately easy to read off what the centre and the radius are for this circle. Okay. But remember what the plan that I said, the plan is to complete the square for x, complete the square for y, that will transform the equation into standard form, and then we can read off the centre and the radius. Here we have our equation. We're going to complete the square with respect to x. So remember, we do x plus half the coefficient of x. So in this case, we're halving 2 to get 1. We're going to square everything and then subtract that 1. We'll do the same thing for the y terms. We have y. I'm going to half that 6 to get a 3. We'll do everything squared. To balance the scales, I'm going to have to subtract off the 9 that 3 squared would give me. And then finally we have this negative 15 that was there to begin with. So if we tidy this up, what do we see? We have x plus 1 squared plus y plus 3 squared is equal to 25. So we've managed to write our equation in standard form. This gives us that our centre, h comma k, is -1, -3, and our radius is 5. We can now graph this on the axes that we've been given. So our centre is -1, -3. There it is. I'm supposed to travel 5 in all the compass directions. So I'll get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I can now sweep out the rest of the circle. Oops. Not bad. What is our domain and our range? Let's record it. The domain, my x-coordinates travel between -6 up to 4. For my range, my y-coordinates lie between -8 and 2. Example 6 here unfolds in a very similar way. You're going to complete the square for x, complete the square for y, and then you, from the standard form, read off the centre and the radius. So I'll leave that as an exercise for you to do. You can check your work if you'd like using the completed notes online. If you'd like to graph a circle on your calculator, without delving too deeply into some of the fancy draw features of your calculator, this is the most straightforward way to do it. You're going to take your equation and try your best to solve it for y. Now we know that circles fail the vertical line test, so we shouldn't be able to solve for y as a function of x, but we should be able to get two different rules that we can piece together to find our circle. So here if we solve for y, we'll get y squared is 49 minus x squared. If we take the square root of both sides, we'll get y is plus or minus the square root of 49 minus x squared. So thus on our calculator, we can go to the y equals screen and say that y1 is the positive square root of 49 minus x squared. That will give us a semicircle. And if we type in as y2 the negative square root of 49 minus x squared, that will give us another semicircle together with the first, which produces the full circle. There's a little caveat here: if you don't do the correct zoom feature, you won't end up with a circle because of the aspect ratio on your calculator screen. Nothing to worry about too much. So here for these examples, you're being asked to identify the centre and the radius. Because they are both in standard form already, we can read off pretty immediately. So for this example in A, we know that h and k are both 0 and 0, and the radius, well, 49 is 7 squared. So the radius is just going to be 7. In this example B, we can read off that h and k are both 1, and the radius is also 1. But by solving for y and typing these into our calculator, we can verify that these centres and radii do make sense. Down at the bottom here, there's a few warnings to consider. So first things first, if when you are completing the square, you end up with an equation that looks like this. I mean, ultimately, if you ever see an equation that looks like this, because these two terms are perfect squares, they will either be 0 or positive. As soon as they are positive, that right-hand side can't possibly be 0. So the only way that we can satisfy this equation is if both terms on the left-hand side are 0, and that only happens if x is h and y is k. Similarly, okay, if the right-hand side is negative for exactly the same reason, there are no solutions. The left-hand side is either 0 or positive. If the right-hand side is negative, we can't possibly solve the equation, so the equation has no graph. There are no solutions. Now, if we take the equality sign in our equation for standard form of a circle and replace it with an inequality sign, there we're really talking about whether or not certain points live inside the circle or outside the circle. So if we look at this first example here, Okay, we have a less than r squared. So that is saying that the point x comma y, when we look at the distance between that point and the centre h comma k, the distance formula is telling us that is less than r. So we should be closer than a radius to the centre, i.e. fully, properly inside the circle. In this second inequality, where we're saying the left-hand side is greater than r squared, that tells us that our point x comma y, when we run it through the distance formula, the distance from the centre is bigger than r. So we should be fully outside the circle. That's something like this situation versus this situation, where your x comma y is inside the circle. So here we have an example. We're asking which homes are within 4 miles of a restaurant located at -1, 1. Well, -1, 1 is right here. I'll use a different colour. -1, 1 is right there. So we want to know what homes are within 4 miles. So inside the circle of radius 4. So let's produce our circle by going 4 along the compass directions. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. That gives us our circle that we can then sweep out. So we want to know which of the 6 houses A, B, C, D, E, and F lie inside this circle, right? Those are the ones that will be within 4 miles of the restaurant at -1, 1. Now, okay, we can eyeball to get a feeling for which we think might be, but F is giving me some pause for concern, because what if my circle has just been drawn really badly and F maybe is supposed to be inside the circle? So the way we can mathematically verify this is to pin down where the houses are and verify which of those points satisfy one of our inequalities. So we have houses A, B, C, D, E, and F, and we just need to test them. So for example, if we test point A, okay, A lies at coordinates 2, 4. So let's check, does that satisfy our inequality? Well, which inequality? We're trying to look at x plus 1 all squared plus y minus 1 all squared, right, because our centre is -1, 1. We want that distance to be less than the radius squared, which is 16. So when we substitute 2, 4 in, I get 3 squared plus 3 squared. That equals 9 plus 9, that is 18, and that is not less than 16. Okay, so the inequality is not satisfied. So A, as the picture pretty strongly suggested, but we've now backed it up with the math, A is not inside the circle, it's not within 4 miles of the restaurant. Let's do one more test together. So let's, I don't know, try E. So E has coordinates 1, -2. We're trying to verify, is x plus 1 all squared plus y minus 1 squared strictly less than 16 for that point? Well, when we substitute in, we get 2 squared plus -3 squared. That is 13 in total, and yes, that is indeed less than 16. So that is true. So E does lie within 4 miles. You can check, so do B, C, and D, but F also, just like A, fails to be inside the circle, just like we suspected, right? A and F really did look outside the circle. We'll end today with one last throwback to geometry, namely to do with tangent lines. So remember, a tangent is a line in the same plane as a circle that intersects the circle at exactly one point. So it just gently kisses the exterior of the circle. Importantly, the fact that we need to know is that a tangent to a circle is perpendicular to the radius at the point of tangency, so where the tangent meets the circle. So in this example here, we can see a tangent line, and yet we can at least have some intuition by eye that it does look perpendicular to that radius. And we're being asked to find the equation of this tangent line. And we're being told the circle is x squared plus y squared equals 25. So h and k are both 0, the centre is 0, 0, and r is 5. And we're being asked for the tangent to be at the point 3, 4. Tangent line, simply a straight line, so we need to find the point slope form for this line. Step 1 is going to be to find the slope of that radius line, right? Because that's our way into the problem. So since one end point is the origin, 0, 0, the other is 3, 4, we know slope is rise over run, so that will be 4 over 3 as our slope of the radius. We didn't want to find the equation of the radius line, we wanted this equation of the tangent line. So the slope of the tangent line is, well, the tangent and the radius are perpendicular. How do we find the slope of a perpendicular line? We take the negative reciprocal. So 4/3 will become negative 3/4 because of our opposite reciprocal relationship there. Finally, we know the slope of the tangent line. We have a point on there, so we can use point slope formula to say tangent line has equation y minus 4 equals negative 3/4 x minus 3. If we wanted to rearrange this into slope-intercept form, we could do so, solving for just y, writing it as negative 3/4 x plus 25 over 4. Example 10 here unfolds in a very similar way. You just need to extract the centre. So h is 1, k is negative 2, r is 5. The issue now is that when we try to find the slope of the radius, we need to do a little more work. Right? Our centre is at 1, negative 2. So there's our centre. We want to find the tangent at the point 5, negative 5. That's down here. So this radius is what we want to find the slope of, because we're assuming that our circle looks something like that. But it's still just a rise over run calculation for the slope of the radius. So we'll have negative 5 minus negative 2 over 5 minus 1, which gives us negative 3/4 as the slope of the radius. Now the rest of the problem will unfold just as above. Take the negative reciprocal, use point slope formula.